Okay, so we had discussed hypothesis testing multiple occasions for a single population. And in this lecture, we had tried to introduce what kind of statistics you use to test the hypothesis for two populations. And in that lecture, we went through key concepts. We're recalling that as well. And we introduced or revisited the t-test statistics. The real idea was how do we approach the problem when we have two populations. All through before then, we have been talking about a single population. Sometimes it's important to look at two populations. What we would talk about today, which we did not talk about last time, was the chi-square distribution, and then some concept about ANOVA and MANOVA, just on the conceptual level so you can understand that. I don't remember that I put this picture here in my further slides when we go further, but this is the distribution of the chi-square that I will come back to. Maybe we'll come back and show you, and we'll look at this picture again together. So a distribution of any function, as you know, is the measured values, and the values on the x-axis here is the x square. So if x is 1, then you have 1 squared, 2 squared, and so on. And then you compute the function value and plot that, and you see that it starts from 0 and increases to a maximum and then falls down. What you should note here is that a chi-square distribution will be in the way that sometimes you can say it has a long right tail, like here. So you can keep that in mind. A function which shows this behavior with a long right tail is how the chi-square function behaves. So what you see here, sorry, is not x squared, but it's the symbol for the chi-square test or the chi-square variable. So sorry for confusing you that this was an x squared, but x to the power 2 here is a symbol. So the input, calculate the chi-square. Just last time, and also as we've seen in our previous lectures, we discussed about hypothesis testing as a way to make inferences about the population based on a sample. And by now, I expect that we all understand that when we are making an inference about the population, we are trying to come to some understanding of the behavior of the population, but we do not really have the population data. We only have a sample of the population. And to do this, we sometimes set up a hypothesis, which we call a null, and an alternative hypothesis, which I also expect you to understand. These are usually contradictory, which means that one statement says something and the other statement tries to verify the opposite. And then we try to look at which of these statements, or we try to look at what the evidence in the sample supports. The evidence sufficiently support the one. Then we can either accept or reject the null hypothesis based on the evidence. So, and of course, we're making a decision when we do that. Some other thing we said in addition to the hypothesis test was that we try to look at the space, so the possible number of errors that we can make. Let's see. Start Grace maybe. So we look at the possible space of errors we can make, and we say we look at it in the form of a table. So all the possible errors that we could make, or the possible outcomes that may occur by mistake. And we said there was a type 1 and type 2 errors. And for the type 1 error, we say it was the error that could occur if we reject the null hypothesis when we actually should not. And it turns out that the null hypothesis should not have been rejected. Then we call that a type 1 error, which is denoted by alpha. The type 2 error was if we fail to reject the null hypothesis when we actually should have. Then we call that the type 2 error, and we use beta. The p-value, on the other hand, was the probability of obtaining an observed sample result, assuming the null hypothesis is true. What is the chance that the observed sample results would happen? So we use p-values to decide that. For a small p-value, we said that it was a strong evidence against the null hypothesis. So it is against the null hypothesis. That means that it doesn't support the null hypothesis, and therefore we should reject the null hypothesis. We can sometimes set a significance level alpha to determine whether to reject the null hypothesis or not. So we compare it to a significance level. There's some kind of an expectation that we set before we do the test. So we can compare the p-value with our expected significance level, and we connected that somehow to the confidence level. So using our p-values, we can then compare that to this level of significance that we had set, and then we can get to a conclusion. When we're doing this kind of tests, we use different distributions. When we're talking about the mean, when I say means here, I mean the mean as in the average value of the population. So different distributions can be used depending on whether the population standard deviation is known or unknown. These are things I would, if I were you preparing for these exams, I would have them on my fingertips. So what are the different assumptions that are made about the population before we can use a specific kind of test? I think it's very central to how you can go about understanding what test to use. So suppose that we know the population standard deviation, which is something we also went through. Then it's possible to use the standard normal distribution. If we, for some reason, have knowledge about the population standard deviation. On the other hand, if we do not, then we use the t-distribution. We also saw this earlier. The normal distribution is also very interesting because it's used if certain conditions are met. And we also know how which conditions there are that we use the normal distribution in terms of the statistics, the Z statistic. Otherwise, we use the binomial distribution. Whichever distribution that we choose, whether it's the student t-test or the Z distribution, it all depends on the factors like the sample size, which we've seen. If we have more than 30, as in the number of instances or responses we have in a sample, whether we know or we do not know the population standard deviation, whether we know that our data is normally distributed or not. All these three factors are very important to determine which type of test to use. I think we've visited this over and over, so please, if you still haven't understand that, review that one more time and at least consult the literature to see that you understand under which conditions which test should be used. We mentioned that the p-values, of course, are central to doing this test. As we said, they help us to determine if the statistic or the statistical error that we are making allows us to accept or to reject the null hypothesis. So we can say, in other words, that this is the probability of getting the observed data if the null hypothesis is true. So what is the chances that what you have looked at, which is the sample, has a certain characteristic similar to the population? Basically, if the null hypothesis is true. The null hypothesis is the statement you make about the sample in relation to the population. Small p-value, then we observe that then there's an unlikelihood. Unlikelihood meaning that it is a lower chance to have, it is unlikely to have occurred by chance alone, and therefore provide evidence against the null hypothesis. So if you get a small p-value, repeating what I just said in a short time, then it is unlikely to have occurred by chance. Basically, the statistic you're making is unlikely to, or the error you're making is unlikely to have occurred by chance. And therefore, you reject the null hypothesis. For us to calculate the p-value, we always need to determine the test statistic and the corresponding distribution. The test statistic here being whether it's the t or the z, and then we use the corresponding distribution, and we use the lookup table to determine the area under the curve based on where we put our significance level. Another way to think of it is that the test statistic helps you to see how far the sample estimate is from the hypothesized value under the null hypothesis. So that's one way to look at it, is you're determining how close or far away the sample is from the hypothesized value. Does the sample reflect the hypothesis you are making about the population? Remember, again, we're doing this because we have made some statement that the sample somehow has a behavior which is the same or which is different from the population. And so when you do the test, is to determine the difference. That's why I mix the word error. How much error are we making by assuming that the sample lies or behaves in a similar way or in a different way from the population? So once we have the test statistic and the distribution, we can use software to find the area under the curve, as I mentioned, which corresponds to the p-value. The p-value would be on the x-axis, and for a certain part of that, we talked about the right and the left arrow, and so on. Depending on how we set up our hypothesis, we need to measure the area under the curve. And because we do not, as humans, calculate that area easily, we can look it up. Given between these ranges, what would be the p-value? Or what would be the corresponding value on the curve to that p-value? So once we get that, it's just to compare that to the significance level, which we said before at the beginning of the test. In that discussion last time, we also talked about the one sample t-test, which basically deals with one sample, as the name says, and with a t-test statistic, and is used to determine whether the mean of a single sample is significantly different from a known or hypothesized mean, population mean. There's a lot of key terms in this, which I hope we understand. So if you do a test that seeks to understand if the mean or the average, a single sample, and here single sample, one sample, is significantly different from a known or hypothesized population mean, then a typical name for that test is called a one sample t-test. To do this test, you make an assumption about the distribution of the data. If the data is normally distributed, or somehow you can verify that the data is normally distributed, then if your data follows a normal distribution, then you have a good statistical foundation, or at least theoretical statistical foundation, that your results can be inferred this way. If your data is not, then you cannot use this, because whatever you get from it cannot be true. In that case, you have to use other kind of statistics. Why do you do this? You still want to be able to understand whether the sample mean, you still want to be able to compare a sample mean to some specific value. What is the specific value in this case? Or for instance, you can be testing if the average height of a sample differs from 170 centimeters. So the specific value that you set in that specific case of a sample that measures the height is 170. And you want to see, given a sample, so the 170 here would be a claim you are making about height in general. Given a sample, you want to see if the average height differs from that value. It doesn't have to be a height. It can be any system or any real world system that you intend to study. We said before that your population should follow a normal distribution. There are other conditions that you can verify, because it's always difficult to know whether a given data collection follows a normal distribution, beside maybe plotting a physical graph and then looking at it. Maybe that's not something that many of you would do, because you probably are not very much versed with the tools that you need. But there are other things you can check. At least you can verify that you have continuous data. You can verify that the sample is randomly selected and representative. We know when we say a sample is representative, know that we mean that the behavior or the characteristics of the population are also in the sample. The population standard deviation is unknown. You can verify that as well if you have no way of knowing this population standard deviation, or at least if you're the one stating and solving the problem. You use the information you have. Maybe you don't know that, or if you're given a problem, you can also look from the description of the problem whether you know the population standard deviation or not. And finally, you have a sample that is small, typically less than 30. So without being able to verify whether your data is normally distributed, you can at least check these conditions. And if you check these conditions, you can use it to determine whether you should do the t-test or not. Then I gave you some examples of where you can apply the t-test beside the height example that I already mentioned in the previous slide. Whether students' test scores differ from a national average. Your specific value there is the normal average. What you want to verify is whether that normal average is applicable to your sample. Remember again here we said that you want to see whether a single sample is significantly different from a non-hypothesized sample. So your single sample is what you've collected in this case. Your hypothesized sample is that it should follow the national average. Or your hypothesis or hypothesis, not sample, is that it should follow the national average. And the national average is a specific value here. Another example could be that you want to check the average daily coffee consumption of a group of, if the average daily coffee consumption of a group differs from 3 cups. So your specific value in this case is 3 cups that you're making the assumption, and you have a sample, and you want then to use your sample to determine how true that value is. based on your measured sample where you actually have measured number of coffee cups that people drink. You then want to infer if that assumption or that specific value can hold true for the population, or the sample will give you a reason to think it doesn't. You will also recall that we use this formula for the t statistics, and I try to explain it. And you can see it has some sort of an error measure between the mean, and we said when you see there, we are calculating the mean from the sample, we use X. And when we calculate the mean from the population, we use this symbol mu here. So the difference between the sample mean and the population mean, meaning that we know the population mean in this case. And in these two examples here, we're talking about the population mean, as you can see, which is the mu. And the data you then collect, you can calculate the sample mean. So in this case, you have the 3 cups of, you have, say, sample which involve people drinking coffee, or a sample which involves student scores. So the X bar would be their mean, and the S will be their standard deviation, which we know how to calculate as the square root of the variance, and the N will be how large the sample is. So then the T, you calculate T, and then you compare that to the critical value from the T distribution table. And then if that absolute value of T here, meaning that you are not looking at whether it's a negative or a positive, you just look at the quantity of what you've calculated. So in this case, -2 will be the same as 2, -1 will be the same as 1, because you are not focusing on the sign. You're just looking at the value. If you take that value and it's greater than the critical value, then it's evidence to suggest that you are making an error that the assumption cannot hold true, and therefore you reject the null hypothesis. And we gave a series of steps you can follow to do this. From the statement of the hypothesis, deciding what significant level in advance, if you want to achieve a certain level of confidence. Sometimes in a problem you're given this, you then calculate your test statistic using this formula here, and then you make a decision by comparing that with your critical value, and then you make a decision. I gave you an example, which I think is clear enough. Also the same things we've just discussed, so I will not go through this example. So we then started talking about the 2 population case. That was the case where you have one population. When you have more than a single population, and under what conditions can you have more than one population? I remember was a question somebody asked. It could be that you are studying 2 groups. This is common in medicine, where you want to study 2 groups of people. One group may receive a certain treatment and the other may not. So you have a population of people who got a treatment and a population of people who did not get a treatment. And you may want to use that sample from each population to draw conclusions about the differences or relationship between the populations of interest. So if you selected people and gave them a treatment, that would be a sample. If you then selected people and you did not give them a treatment, that would still be a sample. These 2 samples represent your assumption about the total entire population if you were doing this on a level of a country or a level of a city. So in that city, you have made an implicit assumption that there will be 2 groups. Some people would get this treatment, some people will not. That's on the level of the city or whatever system you're looking at. Now you are saying that what happens if some people get the treatment and some do not? What will happen to them? How would they make medication, in this case, affect them? But you do not have the complete city or the complete country. So you only have these 2 representative groups, and then you want to study these groups in order to draw conclusions about the big groups in the city or in the country or in the world. What would happen for those who don't take the medication and for those who do? And then you can do a 2 sample test. Either you're comparing the means of the two populations, both with known and unknown population standard deviations, or you are testing to compare the proportions of the two populations, or you are testing if for matched samples where observations are paired or linked in some way. Whenever there is a sample, there is an instance for one, there is automatically an instance for the other if you have a paired sample. So you have tests for comparing means of two populations, tests for comparing proportions of two populations, and tests for comparing matched samples. So in this framework, you do something similar to the case for the one population that we just discussed. You state your hypothesis, you do the selection of whatever statistics that you need, depending on the assumptions. You calculate your p-values, and again, you can use these tables, and then you make some decision about it. So we said there were three cases. One is that you do not know the population standard deviation, or one is that you know it, and then the other one is that you do not know it, and so on. So the formulas are quite similar, except that we are dealing with two variables, 1 and 2, where 1 and 2 represent the populations. So if you have to do a study where you need to deal with two populations, you can easily, from the one population test, you can easily know how to set up the two population tests. Basically, instead of having just one here, in the case of one population, we didn't have one or two. And therefore, this was just the difference between the mean of the sample and the mean of the population. But here we have to look at the variations in the sample means and the variations in the population means, and then take their difference. And instead of taking the variance divided by the normal here, we take the variance, because when you square the square of the standard deviation is the variance, because the standard deviation is the square root of the variance. So when you square that, you get the variance. And so whenever you see theta here, theta here, we are referring to the population. So you know the total number in the, not the total number, you know the standard deviation of the population divided by the sample. No, sorry, this is not for the population, this is for the sample. You can calculate based on your sample, because you not, confusion again. The population standard deviation is known. So this sigma here, not theta, I guess I'm the one who is not who wasn't wake up yet. Sigma here is the non-standard deviations of your two populations known, meaning that we know it. We have a sample, but we also know the standard deviation of our two populations, or our two groups, or our two treatment groups. It doesn't have to be medical. It can also be students in a class, at least an example which is more relevant for you. N1 on the other hand and N2 on the other hand is for the population, for the sample. So sigma 1, which is the population 1 standard deviation, divided by N1, which is the sample 1, the number of data points in sample 1, the number of responses, the number of people who receive the treatment in your sample, the number of students that you use in your sample is the N1 here for group 1, N2 for group 2. So this will give you the approximation error that you're making, and then you can decide how close or different these two statistics are between two populations. When you do not know the population standard deviation, then you replace that with the sample standard deviation. It's exactly the same thing, but you have the sample standard deviation. So for my samples, as I said, the difference between the paired observations are analyzed using a t-test. The approach accounts for correlations between the pairs. Match samples here, I mean to say those are samples where given an instance in one population, there's always a corresponding instance in the other population. And then you have two population proportions there where we have the proportion P1 referring to population 1, P2 referring to population 2, and so on. Then you use this formula. Whether you're comparing means or proportions, as this formula uses proportions, you decide which kind of formula you should use. Then we talked about match samples as well. And we discussed this. You could do a study before and after measurements. That would be a match sample. So if you do a study before and after, it means that group 1 is the before and group 2 is the after, and then you always have a corresponding value between the two groups, as I said. It could also be study characteristics, matching on specific characteristics. The same individual with age in one group, the same individual with gender, so you still have a match sample. You may have natural pairs. If you're doing study on one group is a group of one side of siblings, the other group is the group of another side, or it's a couple, one group is male and one group is female, and then you also have a match sample. I would not spend more time on this. Instead, I think we should go further so we can go to the remaining part of the lecture, because I see that if we do not do that, we'll end up in the same situation that we had last time. Any questions so far? Not that you ask questions, which makes it a one-way monologue. So confidence intervals is one of the things we discuss. And we said confidence intervals provide a range of plausible values for the true population parameter. I don't know if this makes sense to any of you, but what we mean to say here is that the confidence interval is called an interval, and in that interval, we are saying that with a certain statistical chance, the true value lies within that interval. That's basically what the confidence interval tries to do, or the true parameter that we're trying to measure lies in that interval. It's not that the value is 95% accurate or anything like that when we say 95% confidence interval, but rather we mean that the probability that the value lies within that interval is 95%. To construct a confidence interval, we need to know what the plausible range is for the true population. For example, it could be the difference between two population means. We basically have a point estimate, and we look at the plus or minus the critical value times the standard error. So plus or minus here means that this is a pair where one n is small and one n is big, and therefore the value lies within that area or that range. So the point estimate can be a sample statistics. For instance, difference in sample means or proportions. If you have calculated that, you know what the critical value is and the standard error is. The standard error, again, is the statistic that you're using. You can take that value that you want to estimate the confidence in, or that the value that you are estimating, the statistic that you're estimating, and you can add to this section here, and you get the right interval, and you subtract this, you get the left interval. So in the case of, say, you have a variable such as x1, the mean of sample 1, and x2, the mean of sample 2, And the confidence interval would deal with plus or minus t here, which is what we said here, your critical value multiplied by the standard error. And the standard error, sorry, the standard error would be the standard error will be this formula that we use in calculating the t statistic. So if you use that formula, you can verify that this holds true. For the two sample t-tests, we also said there were these conditions that you can verify. And those conditions are necessary for you to determine whether you are using the t-test or you're using the z-test. So for the t-test with unknown population, you have to verify that you have independent samples. So the two samples should not be interdependent in some way. They are independent samples. When you say that two samples are independent, it means that the data points you collect in one sample should not in some sense influence the data points in the other sample. So whatever you select in the first sample is completely independent of the second sample. It doesn't affect. So there's no relationship between these two. The data should be collected through a random sampling method, so all points in each group are equally likely to be used. It shouldn't matter whether you choose this point or that point, so you're doing a random selection. And then the condition for approximate normal behavior is also respected, so the population should be approximately normally distributed, or the sample size should be greater than or equal greater than 30. Then we stopped around this place here. Now I see the time is 21. So we have a few short time to go through the rest. The reason is that it probably would not make sense to go to chi-square without recalling these things. So the conditions for the two population tests, we said that for the Z test with non-population standard deviation, we do not strictly require normality as long as we have more than 30 samples. For Z test with proportions, we need a large sample such that these conditions about the relationship between N1P1 of this, which is basically the proportion of 1 and the population of 1, and also the relation. And if you calculate that and calculate the 1 minus this P1 multiplied by N1, you will have it in such a way that they are all greater than or equal to 5. This was what we said also in our previous lecture. So if you're dealing with proportions, you have a different test. And if you're dealing with the t-test, you use this fact that n is greater than 30. And now I see that there's a wrong symbol here. Formatting error. Needless to say, there are software to do this. We know that. But here is what we intend to talk about today. Now it's 6:22. And my question is, I probably would go over by 10 minutes. Is that okay with you? If there's still anybody there listening to me, is there anybody who has to leave at exactly 6:30?
Yes, so I have to leave.
At 6:30?
Yes, so
I'll
to
try my
prepare for
best.
school.
I'll try my best so we can be able to go through this. So in the beginning, I told you, I showed you a graph that was called, I used the word chi-square. So we haven't discussed about chi-square. So we'll use the last few minutes to see if we can go through that. I showed a graph with a distribution with a long tail toward the end. And that's another statistic unlike t-square. Why and when should we use the chi-square? We use it to analyze categorical data. and it's also intended to be some kind of inference about the population. The population variance to be specific, and relationships between variables. So the chi-square is used to analyze categorical data and make inferences about population variances and relationships between variables. What do we mean by this? First of all, let's look at the the characteristic of what we call a chi-square distribution, which is the graph that I showed you. If a distribution follows a chi-square, if you collected data and plotted that data with your response variable or your dependent variable and independent variable, and the data tends to follow this long tail, which we write long tail. Another word for that is that you have a non-symmetrical distribution. We say that the data is skewed or pushed or influenced to the right. It's non-symmetrical because it isn't one left side. The left side is not a symmetry of the right side. Its shape is determined by the degrees of freedom. Basically, the degrees of freedom here being how much different groups are allowed to vary within that data. The degrees of freedom, if you have data where you have males and females, you have 2 degrees of freedoms because the data can vary between those. If you have other categories, so that's what we call the degree of freedom. Higher degrees of freedom values lead to a more symmetrical shape. We'll come back to what that means. The minimum value of a chi-square statistic is always 0 and can take on positive values only. The graph did not extend to the left. It started from 0 and it extended to the right. Now, suppose that we have we want to do a statistical inference for a single population variance. That means we're looking at the variance for a single population. Variance, we discuss the variance as the differences between our point values or our measurements and the mean value. And then we said because sometimes it can be negative, we squared them. So that was the variance. So if you want to do study the inference of a single population variance, why is variance interesting? Because we want to see how different measurements within a sample or a population are changing. We can always use that information to make a decision about the behavior of that sample. So if you're interested in studying such a relationship, then the chi-square is a good way of looking at it. The chi-square distribution is used to make inferences about the variance of a population. There is a very strong relationship between the variance and the standard deviation. So sometimes you can see that the square of the standard deviation is used to represent the variance. Instead of using 2 symbols, you could have had a different Latin symbol for or Greek symbol for variance. But instead, we use the standard deviation and we square it to mean that we're talking about the variance. The symbol here is not an X, but it's another Greek character for chi, which is this. It's not an X, so do not confuse that. X2 is the chi-square symbol. It has nothing to do with the square of X. And it should be taken as the sample size n minus 1 multiplied by S squared, which is the sample standard deviation squared, which gives you the variance of the sample, divided by the population standard deviation square, which gives you the variance of the population. So it's a very simple formula compared to the others. You simply take n, subtract 1, and the ratio of your population, of your sample variance to your population variance. So this test will help you to determine if the sample variance provide enough evidence to reject a claim about the true population variance. How close is the sample variance to the population variance depends on this error measure here. I hope you understand that well. Let's look at an example. Imagine that we are investigating whether there is a preference for a certain color of cars. We started in the beginning and did a small data collection about preferences. So let's suppose we ask people about their color preference for a car. We ask 100 people and we ask them, what is your favorite color of cars? And then we give them, they either selected red, blue, green, or black. So they were for these choices. So in other words, our uh, variation, or what I just mentioned briefly before about the degrees of freedom, is these colors. Now, 30 people choose red, 20 people blue, 15 people green, and 35 people choose black. This is categories that we are counting, so it's a frequency. Total 100. We had 100 people that we asked. If we were assuming, this is now where would the variance come in? If we're assuming that these are equally likely, we're making an assumption about the population. If we assume that people have an equal preference for these colors, there's no difference at all. We're now going into some kind of a hypothesis here. Then we'll calculate, since there are 4 of them, each one would have a 25% out expectation. So the expected frequency will be 25%. That's why we have 25 all of it, because if we have 4 choices, the probability of each one of that choice is 1 divided by 4, and that is 25%. So our expected frequency will be 25%. This is our observed, and this is what we could have expected if we made the assumption that these colors are equally likely. Now we can use the chi-square to see whether these distributions here is true of the entire population, or is just that we happen to be unlucky and selected the data that statistic and obtain a sample that do not really represent the behavior of the true population. So that's how far away that sample would be from our expectation or our assumption about the population. Suppose there were no color preferences. We'd expect this to have 25%. We calculate the chi-square statistic for what we collected. So for each color, we will calculate the difference between the expected value and the observed value, and then we divide that by the expected value. For example, for the first case, we have 30 minus 25, all of that squared divided by 25, and we have a 1. So if we sum up these values for all colors, then we'll get 9.4. So 9.4 is calculated as the chi-square statistic. We'll then compare this value to the critical chi-square value from the distribution table from the graph that we saw before in order to determine if our observed frequencies differ significantly from the expected frequency. So the procedure is really straightforward. So how far away does the observed values lie from the critical value? We do those calculations and we compare that to the critical value. Just the same way that we're doing when we're doing the one sample t-test. So to determine how we use this, we'll use the goodness of fit, which is a way to assess whether the observed frequency categories in a sample match the expected frequencies based on a specific distribution. The specific distribution here is the assumptions we made about the population, saying that all the colors were equally likely. How far away we are testing whether the observed frequencies of the categories in the sample match our expected distribution. And based on this, we can determine if the sample fits with the theoretical model or it differs. The theoretical model, again, is our assumptions about this 25% when we said they were equally likely. How well does this agree with this? So we use the goodness of fit for that. We also can test independence to examine the relationship between two categorical values and determine if there is an association between the variables or if they are independent of each other. So we can do a test of independence to determine the relationship between two categorical values. Two categorical values here could be two different colors in this case, and determine if there's an association between the variables or if they are completely independent. So to sum it up, the chi-square distribution and its associated tests are widely applicable in research. For example, whether it's about genetics, analyzing the frequencies of gene variations, market research, examining consumer preferences across different demographics, or healthcare, investigating associations between risk factors and disease prevalence, and so on. And there at the time is 6:34 now. I was promising to go over time a little bit. I know some people might leave, then you will still have the video. I will introduce you to another type of test, but on a conceptual level. Just we are aware of those concepts. Now, I don't know, Madam Rama can correct me here. I think you might be expected to also be able to do these tests in a practical data set. Regardless, the starting point is to know what the concepts are and what they represent. So for ANOVA, for the chi-square, we've seen that we're looking at categories. For ANOVA, we're looking at continuous data. And what is ANOVA in the first place? Well, ANOVA is the analysis of variance, as the name is a short form for analysis of variance. So the chi-square test allows us to study or analyze categorical data. We know that we also have continuous data. Instead of categories of a car, for instance, preferences about categories, we might look at how average fuel efficiency varies across different car models, which can be a very real world. It can be a real world problem that we want to see the average fuel efficiency across different models of cars. Then we have continuous data because average fuel can be seen as continuous. It can't be any number in practice, any real number. So the way to do this kind of analysis is using something like ANOVA, which allows us to compare the means across multiple groups to determine if observed differences have any statistical significance. So if you're asking an exam to describe ANOVA tests, you have to keep in mind that, number one, it is a statistical test used for continuous data. Number two, you use it to continue to compare the statistic across more than just a single group. And in this, for example, you can compare the means across the two different groups. And the purpose is to determine if the variance is significant, statistically significant. So you examine the differences between means, as I've said. Let's look at another example, testing the effectiveness of 3 study techniques. So in this case, the 3 study techniques will allow you to have more than just a single group. Flashcards, as an example, flashcard is basically using cardboard. I think you understand this better since they're study techniques and you're doing education. Space repetition summarization on exam scores. So ANOVA can help us determine if there is a significant difference in the average exam scores across these techniques. The idea is that you assess whether the variation between two groups is greater than the variation within each group. In order to do this, you could do this using something called a one-way or two-way ANOVA, where one-way involves a single independent variable with 2 or more levels. You have a single variable and you want to, and you have two or more levels or groups that you want to test that variable. For instance, if you're talking about study technique as the variable, and then the groups can be flashcards, space, repetition, and summarization. If you're talking, another alternative is that you can use a two-way ANOVA to examine the effects of two independent variables on a dependent group. So two-way ANOVA, you have two variables. One-way ANOVA, you have one variable, multiple groups. Two-way ANOVA, you have two variables, multiple groups. For instance, extend the study to include prior knowledge. Here we are saying that we have a single study technique. So if we add prior knowledge to the study technique, then we have two variables. So we're looking now at the study technique. We're looking at prior knowledge that students have. Suppose we want to study and collect information about that. And then we want to look at this in relation to different uh, uh, groups, flashcards, space repetition, and summarization. So the key point here is that we have two variables and we have three groups. So then we have a two-way ANOVA. What if we want to investigate the effect of study techniques and prior knowledge on multiple dependent variables, such as exam scores and study time? So in this case, in the previous example, these were independent, and now here we have independent. Multiple dependent, sorry. So this requires multivariate approaches, and this is called multivariate analysis of variance. And then you have MANOVA. So in addition to just studying either one for one way or two variables on more groups, you could also have the situation that you have the multiple dependent variables between these groups, and therefore you talk about, so in some sense you have multiple multiple variables that you want to study on two groups which have multiple variables as well. So you have MANOVA as on a conceptual level to understand the idea and the concepts. So MANOVA extends ANOVA to handle multiple dependent variables simultaneously and provide a comprehensive analysis of that. And then another example is that we would like to assess whether the combination of a study technique and prior knowledge has a significant effect on both exam scores and study time. So we have more than two study techniques here, and we have two different variables that we want to study on each of these groups, exam scores and study time. This way of analyzing information provide us with a more holistic understanding of the relationship between independent and multiple dependent variables, reducing the risk of type 1 errors, which we discussed earlier. This is suitable for analyzing the effect of one or more independent variables on a single continuous dependent variable. For example, comparing exam scores across different techniques is appropriate for ANOVA, whereas for MANOVA, it is appropriate for studying the effect of independent variables on multiple continuous dependent variables, such as analyzing the study technique and prior knowledge on both exam scores and study time. The way you do the test, key test for ANOVA is that you use that to compare means across multiple groups for a single continuous dependent variable. One way ANOVA involves one independent variable, while two-way ANOVA involves two independent variables. And MANOVA extends ANOVA to analyze multiple dependent variables simultaneously. Choose ANOVA for single dependent variables and MANOVA for multiple dependent variables. So you really have to read a little more about these. I just introduced them to you so you know that these techniques are necessary and covered in the scope of the course. I know I have exceeded by 3 minutes what I said 10 minutes, and I will leave the word to see if Madam Rama would like to add something to this. I know I took her unaware on this. What would you like to emphasize? Anything before we round up and everybody goes to their daily business for today? Or maybe she left. Or am I talking to myself?
You are not talking to yourself.
Okay, okay. So I know we exceeded time. Do you have any one short few word to ask to add? And is there any question before we move on? I will publish. Not. I would not publish this lecture on the course homepage. Rather, I will publish a different lecture because this one is there already. Has been there for the last 2 weeks. I'll publish something we will discuss, and I hope tomorrow we can discuss that in the morning, which is sort of going through the overall course. I know I'm informing you late now, but tomorrow is Saturday, so is there any question, please? Everybody's left even.
There are, I can see two of